All right, so welcome again to the real-time DSP class here at the University of Texas at Austin. This is lecture 5, part 3. So we've talked so far about a couple things. We've talked about many roles for filters, spectral analysis, spectral shaping. We've talked about convolution, which is what filters do in the discrete or in the time domain, discrete or continuous. We reviewed Z transforms, region of convergence, and we've talked, and we're going to move into some filter work now. So, some filter design and some demos. We left off with the. We didn't cover this part yet, right? The Fourier fundamental theorem yet. Okay, so the fundamental theorem of linear systems, linear time invariant systems, is pretty important. Fundamental is a key word. I had a professor at my undergraduate school who called us a two-star problem, or two-star wake-up problem if it were 8 in the morning. So this is a fundamental theorem of linear systems. And if a complex, so this is important, so if a complex sinusoid were input into an LTI system, then the output would be a scaled version of the frequency, the input would be scaled by the frequency response of the LTI system. And the scaling is evaluated at the complex sinusoidal frequency, that is to say, whatever the frequency is of the complex sinusoid. And this description assumes that the sinusoid is two-sided in time. So the scaling may attenuate the input signal and shift it in phase. It's possible this attenuation is so severe it actually zeroes out that input signal. So if the input signal is a two-sided complex sinusoid, so if the input signal were, for example, x of t, then we know that the Fourier, this is two-sided, so the Fourier transform looks like what? Two impulses, one at f naught and one at negative f naught. And the area is a half, since I'm in hertz. And that's it. So it's only, the signal, which is two-sided, has just one frequency component at f naught. So it may get through the LTI system and it may not. If it gets through the LTI system, the amplitude of the cosine may be reduced, could be increased, and the phase could be shifted. There's an example in continuous time in handout F in the reader. The example in discrete time is to let the input be a sinusoid. Now this is a more general version of the sinusoid. And we'll look at both versions soon. So this version we can write as a cosine and sine component, so we can certainly write this as cosine omega n plus j sine omega n. So it's an oscillating signal with one frequency, and it's two-sided, but in discrete time. All right, so let's look at what happens. So let our input be so this is a real valued cosine. This is a real valued sinusoid, and we'll talk about how to extend this to that case, but it applies as well. And but the statement here is actually for a complex sinusoid. Okay, so complex sinusoid, cosine omega n plus j sine n. We put this through an LTI system. This LTI system has an impulse response, h of n. So in the time domain, the output of the LTI system is simply a convolution of the input and the impulse response. All right, that's just it. Okay, so it's x of n convolved with h of n. So doing convolution, we hold one signal in place. We'll hold the impulse response in place. We'll flip and slide the input about the impulse response. The Okay, so we have a placeholder variable of convolution, which is little m. We're going to sum over all possible values of m from minus infinity to infinity. We're going to flip and slide the complex sinusoid. But the flip here is due to the negation of m, and the slide is due to little n. Slide or shift is due to little n. And again, n is the outer variable in discrete time. So we sum over all the values, and what's kind of nice is this exponential can break up pretty nicely because of the minus sign here. We can break up the exponential into two pieces. So we can take e to the j omega n minus m and break this up into e to the j omega n and e to the minus j omega m. Now, in the summation here, my placeholder variable is little m. So the term that involves little m has to stay inside the summation, but the term that involves the other term here doesn't involve little m at all. It's independent of little m. So e to the j omega n can be pulled out to the front of the summation, can be pulled outside, because it does not depend on little m. And we get now the notion of what an LTI system does in the frequency domain. And there's a caveat here that you have to have the Fourier, so what happens, my input, this is my input signal, right? That's my input signal. So in the time domain, the output of my LTI system, given the input, which is this two-sided complex sinusoid, is simply the input scaled by the frequency response of the LTI system. So that capital H of omega is simply the result of this summation. And the summation is the definition of the discrete time Fourier transform. And we can compute that discrete time Fourier transform sometimes through the Z transform. Okay, the Z transform, and then substitute Z equals to the j omega. Otherwise, we might have to compute it directly using tables and properties of the discrete time Fourier transform. Now, we haven't covered the discrete time Fourier transform, and neither has a prerequisite class, so this is going to be new. We're not going to use it very much other than to usually get the Fourier transform from the Z transform. But on homework, there's one case where you have to go look up a transform pair. Okay, so this is the frequency response of the LTI system. And it is true, it may not exist. There's some weird cases that we don't have one. Happens. Okay, but if we have one, and we certainly have one for bounded input, bounded output stable systems, because we can convert the Z transform into the Fourier domain. Okay. So anyway, this is again, back to the statement at the very beginning. This is the mathematical description here. But again, if a complex sinusoid were input into an LTI system, then the output would be the input scaled by the frequency response of the LTI system. True both in continuous time and discrete time. So this is filtering. This is why filtering is interesting, because if I have an LTI system and I have a frequency response, then by choosing the impulse response, I can get a certain frequency response, or I can try to target a certain frequency response and design my impulse response in the time domain. But this is the key. So certain frequencies will pass through, certain will get rejected. So if the frequency response goes to 0 at a particular frequency, that input frequency is removed by the LTI system. If the magnitude of this frequency response were 1, and the phase is 0, then this input signal, this input frequency passes through unchanged. And there are variations, of course, in between. Okay? So h of omega is a complex valued function of a real variable omega. So we can write h of omega as a magnitude and a phase. As a magnitude and a phase. So that means that, again, if the magnitude is 0, then that frequency is zeroed out, doesn't get through the filter. This corresponds to a phase shift. So if you look at what happens in the output here, the output is scaled by the magnitude response at frequency omega and shifted by the phase response at frequency omega. Okay, so up until now, we focused mainly on the magnitude response when talking about spectrum, but now we're going to bring phase into the story. And that's part of homework 2. So in other words, this response is now going to be, if I combine all this, I get the magnitude of h times e to the j omega n e to the minus omega n minus j times the phase function. Let me erase the extra term here. So again, the output scaled in magnitude by the magnitude response at that frequency, shifted in phase by the phase response. Should be a plus here. Shifted in phase by the phase response of the LTI system. This is fundamental. This is what filtering is all about. Questions on this one? All right, so let's apply this to the real-time cosine and sine, the real-time case, the real valued case, which is what we would build in lab. So in lab, we're not going to build a complex sinusoid. We're going to build a real valued sinusoid, a cosine or a sine. We'll generate. That's also lab 2. You're doing this as well. So there's some interesting properties that we're going to put into play here to make all this work. So for the real valued impulse, for a real valued impulse response, there's a very interesting property. I always have to look this one up. There's a very interesting property in Fourier transforms in that the Fourier transform has a conjugate symmetry. Now, so what does that mean? It means e to the minus j omega is the same as the conjugate of both the function value, which is a complex number, and the argument. So what does that mean? It means that the magnitude response is even symmetric about the origin. We're familiar with that. So I have to show you the positive frequencies, and you can show me what the negative frequencies are. It also says that the phase response is what kind of symmetry about the origin? It's odd symmetric. Okay? So again, if I show you the phase response in positive frequencies, you can recreate the phase response in negative frequencies. So I have to tell you half the story, and you can create the other half. Now, some other things which is kind of interesting. Now, if we look at using this fundamental theorem from the previous slide, if I take complex sinusoid, e to the minus j omega n, and I add to it its conjugate, then I get 2 times the cosine, right? And we can do that just by expanding e to the minus j omega using Euler's form as a cosine plus j sine, like we had done on the previous slide. So this just collapses down to 2 times cosine omega n. So that's nice. So because I know what the answer is here from the fundamental theorem of linear systems, and now I can use the additivity property really of my linear system. So now I can put in a 2 cosine omega naught, and it's the same as putting in these two-sided complex sinusoids. This is a 2-sided cosine for all n from minus infinity to infinity. Again, this is theory. We'll get to the practices. We're getting closer. All right, there's a derivation here about that the same fundamental theorem applies to the case I put in a real valued sinusoid, a cosine or sine, into an LTI system. The same phenomenon happens. So I put in a cosine, so here's continuous time. I put in a cosine of fixed frequency. That fixed frequency is capital omega in radians per second. This is fixed. And it's in radians per second. The output is the cosine scaled by the magnitude response of the LTI system and shifted in phase. Just like we saw it in the complex sinusoidal case. No change. Same thing holds in discrete time. The same theorem as in discrete time. And the same holds up as a consequence for an input that's a cosine at a fixed frequency. So now our fixed frequency is omega. So this is fixed, and this is in radians per sample. This is nice for lots of reasons. For one, in theory, what this lets us do, and we can do that, well, this also works for a one-sided cosine, and it also works for a finite, a cosine that's observed for a finite period of time. All right, so let's talk about, back to the theory. So we have a two-sided cosine. Now what this means is that I can put in a cosine at, say, pi over 2 radians per sample and look at the output. I can put an input in at, say, cosine pi over 4, pi over 8, 3 pi over 4. And I can build up I can determine the magnitude and phase for every frequency that I can put in. Now, it's very tedious. I have to go through all the frequencies one at a time. I'd never finish, right? That's an uncountable story. But in theory, what I can do is pick off a few points, put in a cosine of pi over 2, see what happens. I can look at the output and directly read off the change in magnitude and the change in phase. I can put in pi over 4, put in 0 for the DC response, and I can build up samples of the frequency response, both in magnitude and phase, and I can just interpolate between the points I have to get an estimate of the magnitude and phase response. And this is what we're going to do in lab. And this is lab 3 coming a little bit later. Now, lab 3 will send a cosine of finite duration through and see what happens. And you know from homework that if I have a finite duration cosine, then I have a lot of energy at this frequency, but I also have other frequency content, but it drops off or decays pretty quickly. But you'll see a very similar phenomenon that you can put in a finite cosine, and you can look at the output and compare the two on the oscilloscope, if you had to do it with rack equipment, and manually estimate the change in the magnitude and the change in the phase by superimposing the two signals. Okay, so the oscilloscope would be in continuous time. Sorry. Right, so here are one example of a magnitude and phase response. So again, frequency response. So again, our system responds to a complex sinusoid. E to the j omega n is for all possible frequencies, is our frequency response. Now, in continuous time, we have all the possible frequencies from minus infinity to infinity to worry about. It's a big, that's just a lot of line. It's a whole real line, right? So in practice, we're not going to plot the whole real line, but we're going to plot some frequency range of interest based on our application or what we're trying to do with the filter. So we'll plot some range of frequencies. Now we can, that would be continuous time. Here I have discrete time, radians per sample, and the good news with discrete time is that I don't have to worry about frequencies from minus infinity to infinity, although they're there, because why? What do I have to worry about? What range of frequencies do I have to worry about in discrete time? Minus pi to pi. That's right. That's all I need. And the reason for that is, if you remember converting continuous time frequency to discrete time, there was this conversion. Right. So F naught is the, if you remember, F naught was the frequency in, this is the frequency in hertz. And Fs is the sampling rate. And this is periodic with period 2 pi, because this is going to correspond to a cosine. Right, this will give us a cosine omega naught n. Go ahead.
So are you saying that because of the fact that we're always choosing some sampling rate, the frequency response will always be measured as a kind of as a proportion of 2 pi? Like
Correct. That's right. Because once we pick a sampling rate, we're going to measure the frequency as a interval of 2 pi, and then if we need anything else, we can just periodically replicate that. So if I tell you the frequency response between minus pi and pi, you can get everything else by shifting by 2 pi to the right and shifting by 2 pi to the left. All right, so this is our discrete time cosine, and we got there by sampling and so this way we're going to sample. So this frequency in continuous time F naught becomes this frequency omega naught in discrete time. So that's one, so there's this formula for one, but I also know that this is going to be periodic with period 2 pi. So I know that eventually when F naught gets to be half Fs, what is that? So omega naught takes some value. So what do I know? I know that, through sampling, let's put it on the side. So from sampling, sampling captures the following frequencies from minus half Fs to half Fs. And the reason for that is simply the sampling theorem, that Fs is greater than 2F max. So what that tells us is that F max is less than half Fs. Right, that's just a byproduct of the sampling theorem. So what that means is our sampling will capture frequencies from minus half the sampling rate to half the sampling rate. And whether those endpoints get included or not is an interesting discussion. We certainly need to include one of them for the periodicity to hold. But if we include both of them, the periodicity doesn't hold anymore. We have to include one of the endpoints to be strict about this. I don't care which one you want to include. If you like the other one, that's fine. Okay, so I have to include one of the two, but not both. Okay, now that's in hertz. Now half the sampling rate corresponds to what content in discrete time? What omega naught?
Like up to pi.
Up to pi, right? So you put in F naught to be half Fs. Fs cancels. Half times 2 is 1. I get pi. Right? So half Fs maps to pi, and minus half Fs maps to minus pi. So the discrete time frequency domain is periodic with period 2 pi. So in doing filters, we tend to plot minus pi to pi, but I don't really need to do that because if I just show you from 0 to pi, you can get the rest from the even symmetry of the magnitude response. And the phase response, again, has odd symmetry. I tell you the extent from 0 to pi, you can tell me what happens from 0 to minus pi. All right, so here's an example of a low-pass filter, and it's going to pass low frequencies and attenuate high frequencies. So here's the pass band. So in this range, we're going to pass frequencies, even though it's not exactly 1. We allow a little bit of tolerance in there, a little bit of variation. So we're going to make sure that as long as the magnitude response resides in some interval close to 1, and including 1, then we call that the pass band. At some point, just from applying a threshold, we'll find out where the stop band is. Okay, so there's our stop band. Again, this is somewhat arbitrary. I have to pick a threshold. Sometimes I know it from the design specification that I might be given. Okay, but eyeballing this, I said, well, at some point I have a stop band, which means I'm reducing dramatically those frequency components as they pass through the filter. Remember, this is the filter's frequency response. I then have this band in between. We call this the transition band. And really, the magnitude response can be almost anything, except we don't want it to exceed what we allow in the passband. So really, the magnitude response in the transition band is anything between 0 and 1 inclusive. It's almost a don't care region. It kind of is, except that we don't want it to go above 1, because now we're amplifying frequencies in the transition band. That doesn't make a lot of sense. Because then it actually would be another passband. That doesn't make a lot of sense. Anyway, so the transition band has some flexibility. All right, so that's the magnitude response. Now the phase response could be linear or not. Depends. In certain special cases, it is linear, and you'll see this in homework 2, problems 2.1 and 2.3. So 2.1, you have the averaging filter, first order difference. There's a linear phase. We'll talk more about that. And 2.3, you're designing a bunch of linear phase FIR filters. All right, so low pass filter. Again, we're going to pass low frequencies and attenuate high frequencies, kind of in the definition or embedded in the wording here. So a high pass filter would do the other way. It would kind of do the dual of this. High pass filter would pass high frequencies and attenuate low frequencies. And we've already talked about an example, right? What's an example low pass filter? Averaging. An example high pass filter? First order difference. Exactly. All right. Now linear. So to get linear phase, I have to have it, and we'll get to the derivation in a second. I must be an FIR filter, but that's not enough. Not enough for linear phase. Necessary. Next step, and the impulse response has to be either symmetric or anti-symmetric about its midpoint. So that seems a bit constraining, but it turns out a whole lot of filters satisfy this condition. A whole lot of FIR filters. The averaging filter satisfies this condition. First order difference satisfies this condition. Okay, now, the last thing on this slide is delay. And remember last time I mentioned a delay of a half sample, and that, not last time, I guess that was in part 1 of lecture 5. I mentioned the averaging filter had a delay of a half sample. And it seemed to bother you. It still bothers me after all these years. Because we're on an integer grid, how can you have a half sample delay? But it happens. So the delay is defined, this is called the group delay, as the derivative of the phase negated. So I find the slope and negate the slope at any point in omega. Now the good news is with linear phase response is the slope is constant and negative. And that means that the delay is a fixed value for all frequencies. In other words, it looks like an ideal delay in terms of its phase response. The magnitude response may not be, for an ideal delay, what's the magnitude response? You remember what that was?
What a neat,
Isn't it like
It's a straight line.
Yeah.
It's a straight line, right? So we'll go back a couple slides for that. Right, so here is the ideal delay. Magnitude response is 1. It's constant over all frequencies. And the phase response is linear. Right? And you can read the delay right off with a slope of -1, it means the delay is 1.
what if the phase is
The phase is not linear. It means that the delay experience through the filter changes with frequency. Now, it's interesting. That can be a very interesting effect. So think about audio. So in audio, you've got, so for example, you've got percussive sounds running into high frequencies, and you have more of the piano and so forth. Well, it does have harmonics, but in lower frequency bands, a lower frequency range. So you can imagine if your filter somehow delayed the high frequencies by like a second and delayed the piano range or the keyboard range by a millisecond, your drums would be way out of sync with your music. Okay, so in audio we can tolerate a little bit of that, but you have to be careful how much delay difference you're enabling. If you have one channel audio, if you have two channel audio, you can get away with a little bit more variation. But so in practice, for an FIR filter, we can design it so that we get this fixed delay. But an FIR filter where the impulse response is not even symmetric or odd symmetric about its midpoint, doesn't have linear phase. And infinite impulse response filters, the ones that we can build, do not have linear phase. It's an issue to consider. It's not, not the only issue but it's one of the issues to consider when choosing which kind of filter you'd like, finite impulse response or infinite impulse response. Okay, so in homework 2, I've asked you to design filters, and this is and I give you a specification that looks like this. Almost. I have to fix one thing here, which I will. So what I did in homework 3 is I gave you a magnitude response I wanted to have, and I gave it to you in intervals. Now, in the homework 2.3, it was a bandpass filter. Here I'm giving you a low-pass filter. So in a low-pass filter example, I tell you the passband frequency and the stop band frequency. I tell you the stop band attenuation that I want. And I tell you the passband ripple that I'm allowing. Now, in IR filtering, so this is actually one. For FIR filtering, we actually allow the variability to go plus or minus 1 in linear units. Now, a more common set of units for filter design is not linear units, but dB. Okay, so if a linear unit is 1, which now will be here in the FIR case, linear unit of 1, what's the dB for a linear unit of 1? 0. So in dB, this is 0. So 0 dB should be in the center of our passband of your filter that you design. Okay, now problem 2.2, you are designing a low-pass filter. All right, so that's 1. And then the ripple, if I tell you the ripple is 1 dB, it means that this interval is plus or minus 1 dB. So I go from minus 1 dB to 1 dB when designing the filter. And I'll give you an example of that in just a second. And again, the transition band remains unspecified, but you should sanity check what you get back to make sure that what happens in the transition band does not exceed 1. I'll give you examples later in lecture 6 that we'll see that doesn't hold. Yeah.
I'm kind of confused by this drawing.
Yeah.
What exactly is it representing?
So it's a low-pass filter, so it means I want to pass frequencies from 0 to omega p, which means I ideally would like to have no change in magnitude. So the linear unit would be 1, and in dB, 20 log 10 of that would be 0. And then there's another range of frequencies from omega s, our stop band frequency, to pi, which is the maximum frequency possible in radians per sample.
For the transition band, what is it like up 1 feet per minute?
Yes, but when we give parameters to a filter design, so the question was, can we explicitly exclude the magnitude response of the transition band so it doesn't exceed 1? That's not part of what we tell a filter design algorithm. You have to sanity check it.
Oh, okay.
You're responsible for that one.
All right.
Okay. And it's good. You should always check any answer returned by a computer to make sure it's reasonable, right? And we're going to see very quickly that all these filter design algorithms don't give you back a filter that meets your original specification for the FIR case. I'll show you an example of that in a second. So I asked you on homework to give me 3 different filter designs in homework problem 2.3. This is due on Monday, and it turns out each of these 3 gives you an FIR filter with symmetric impulse responses about its midpoint, and it's going to have linear phase. Each one of these will give you linear phase. Go ahead.
window in Remez algorithms, it lets you specify, I want the minimum order possible to meet these specs, but on
Right.
the least squares, you have to specify the order yourself.
You have to search for an order. That's correct.
So you need to tweak the order until you can find something that is as small as possible while still meeting your specs.
That is correct. So I'm asking you to find on the homework the smallest order filter, and the order so the order means the number of zeros,
Yes.
and the number of coefficients is the order plus 1. Right? If I factor a quadratic polynomial, which has three terms, I get 2 roots. Right.
Okay.
So here's the FDA tool in MATLAB. So I asked you to design a low-pass filter, and here is what I just showed you on the slide, right? This is the target, this is the pass band, this is the stop band, here's the stop band attenuation, and here's the pass band, I say variability, if you will. The ripple is actually twice, the ripple would be, double the ripple gives you that range. Go ahead.
Why don't you, why do you care about the magnitude of the pass band upper?
Well, we're going to see, there's lots of reasons for that. Again, the ideal is you'd like to have exactly 1 in linear units or 0 dB. If you could have a flat pass band, it would be great. We can't give you a flat pass band. So it's going to wiggle. We're back to wiggles now. It's going to alternate. And we want to keep it in that small stretch so that those frequencies appear to have been passed. So in audio, they sound like they've been passed. In imaging, they look like they've been passed. If you let that variability grow too big, then you're going to be amplifying some and attenuating the others, and you're going to hear a difference. So we're going to tie this into quantization later, that it does relate back to quantization that you're doing.
So like clipping?
This is going to have to do with what the least significant bit can represent in your quantization. You're assuming no clipping when we'll do the analysis later. That's lecture 8 slides. It's coming. All right, so so I asked you to do equal ripple is another name for Parks-McClellan, Remez exchange, lots of different names for the same thing. So the minimum order, let's see what I need. I need low pass.
Can you like pass parameters into this? Like,
Oh, I'm going to do the example that we're going to do in class. So in homework, it's a bandpass example. Go ahead.
oh, I was going to say, can you pass the parameters into this not using the GUI?
Correct. Their command line interfaces too, but it's not as clean as this. You're going to have to go dig in finding the right MATLAB command. You don't want to use the graphical user interface. So sampling rate on the homework was 200. First stop band frequency was 1. First pass band was, sorry for the beeps, and pass band was 6. Second pass band was 40. Last stop band was 45. Pass band was 1 dB. Stop band was, do you remember? 40. Good. Okay, so good. You are working on it. All right.
Wasn't the stop why did you choose the stop bands, the stop frequencies to be 1 and 45?
I chose it, and I gave some explanations this was an ECG filter, and I gave some explanations.
Yes.
So there's some frequencies close to 0 you want to eliminate.
Yes.
So that explains, I want to stop frequencies from 0 to 1, low frequencies. The pass band, I have a power line frequency that's going to interfere at either 50 hertz or 60, depends on what country I'm in. So I put that in the stop band. And the last thing is that the transition band is about 10% of the bandwidth of the filter.
Yes.
That's a rule of thumb that we'll see play out many times. So that kind of set. So the bandwidth here is 34 hertz. 10% of that's 3.4.
So you could go as low as like
5
40,
and
43.
do 5 and 42 or something or
Nice.
whatever. So I just want to give something that
Yeah.
gave you reasonable filters to work with. All right, so let's design this. So here's 57th order FIR filter by the Parks-McClellan or equal ripple design method. Now, does this meet the specification? No. Where does it fail?
It doesn't meet the 40
Right, so right here, so 40 dB, so all these ripples should be below or at minus 40 dB, and they're not. So I gotta do something. Now, so the stop band's a problem. Is it a problem over here? It's also a problem on the low frequency stop band. Okay, so I can do two things. Either I can increase the order, or I can make the specification more difficult, which will in turn increase the order, which is what I'm going to do. So I'm going to crank up the stop band frequencies to 43 and 43. We'll see what happens. Maybe it will do it. Okay, the order is a little higher. It's 60, went up by 3. But let's see if it meets specification, at least visually. Looks pretty good. All right, so at 45, it should be below 40, and it is. And in the stop band, it should be below 40, which it is. So that's good. Let's try the low frequencies. Hard to say. Oh, there we go. Good. So at low frequencies, we're below or at minus 40 dB. So we've met specification. Now, also from the same menu, you can get pole zero diagrams and impulse responses and all kinds of things, right, under analysis. There's your impulse response, even symmetric about the midpoint. You get, oops, give me the print. Sorry. Under analysis, I can get pole zero plot. Whoa. Okay, so lots of zeros. Here's where they are. We'll talk about why this makes sense a little bit later. But I will show you that that's your stop band. Zeros are on the unit circle. So then you're right. Now for the other cases, I asked you to do least squares and window. And so for least squares, you're going to have to search. And you're going to have to fiddle with the parameters to make them different from the specification that I gave you, make them harder to meet. And that will let you get the order down. That seems weird in least squares, but least squares has a real problem. It doesn't do a very good job at meeting the magnitude response specification at the stop band frequency. So we can trick the algorithm by moving the stop band frequency into the transition band. Make it say 43 hertz or 44 hertz. And then actually we'll get the filter order down, surprisingly. And then last is the Kaiser or window method. Go ahead.
Wait for a minute to use file and generate MATLAB code.
Absolutely, you can export the filter design to MATLAB. The MATLAB is still, I ran this from MATLAB, so all I did is I typed in FDA tool to run this. FDA means filter design and analysis. And you can get data from the FDA tool back into MATLAB. So you can get the impulse response and then type in freq z to get the magnitude and phase response. So freq z is a good function to know. We use it a lot in this homework. Right, so freq z is just, give me, the simplest use of it is just give me a vector of the impulse response. That's the first argument for an FIR filter. And we'll give you the magnitude and phase as plots of the frequency response. And PZ plot would be the other one that's useful for pole zero plot for homework 1, 2.1.
DNA or vectors here?
Yeah, okay, so for the more general case, this applies for both FIR and IR filters. For IR filters, I have now a denominator. I have feedback coefficients. We'll get to this. So I can use the freq z. So that B is my feed forward coefficients, my FIR portion, and A is the feedback coefficients. So this also works for IR filters. For now, we don't need the other two arguments, really. If you need the second argument, you just put a 1 in there for an FIR filter, and it works fine. N is the number of points you want to use for sampling the magnitude and phase response for the plot. So if you need to increase N, then you would put 1 in for A and then make it a larger N. I forgot what N defaults to. It's pretty big. Is it 5? Okay, good. It's pretty big. All right, so let's finish out. All right, so let's do a couple of simple examples that are getting pretty familiar now. And for good reason, these are very commonly used filters. All right, two-tap averaging filter, which you're doing again on 2.1 homework. So this is a normalized averaging filter. So I have simply the output is the average of the current and previous input value. The impulse response, this is basically let. I'm in the wrong mode, sorry. So this is just let the input, be the discrete time impulse and see what happens, right? There's impulse response. Frequency response, I can take the Z transform and then substitute e to the j omega. So the Z transform here, which you did on homework 1, and this is true for, and this is for Z not equal to 0, just to avoid the division by 0 case. And now I can substitute for Z e to the j omega to get the frequency response. So this is just the frequency response where I've substituted Z equals e to the j omega. Now, it's interesting, so here's the impulse response, right? Half-half, and the rest of the coefficients are 0. Here's the tap delay line representation. I have 2 taps, 2 coefficients, each are valued 1/2. I have 1 delay block. I can factor out, interestingly, e to the minus j 1/2 omega, which corresponds to the phase shift for a half sample delay. Weird as it is. All right, so here I factor that out, and I get the 2 remaining terms is e to the plus j omega over 2 and e to the minus j omega over 2. And the nice thing is that this term collapses down into cosine, 2 cosine, which I scale by 1/2 and get a cosine. So it collapses down nicely. And then I get a phase term, which is linear in slope, and the slope is minus 1/2, and that means the delay is what? What's the delay? Half sample. Right? So we can read that right off the phase response. So the magnitude of response looks like the cosine omega over 2. So if we were to plot the magnitude of response, it's the cosine omega over 2, so cosine of 0 is, cosine of omega over 2 when omega 0 is 1. Cosine when omega is pi, cosine omega over 2, omega is pi gives me 0, and same with minus pi. So the magnitude response something like that. Not a great low-pass filter. It's got a pretty wide passband. But if you add more and more terms, you get a more and more narrow passband. That's two-tap averaging filter, linear phase. Now, first-order difference, you do the same kind of analysis. Input-output relationship. It's now the difference of the current input and the previous input divided by 2. Impulse response looks very similar, except I have a negative sign instead of a positive sign. Same story for the frequency response. And I can also factor out the midpoint, or the phase shift corresponding to the midpoint. Now, what's different is I get e to the j omega over 2 minus e to the minus j omega over 2. This collapses down to 2 times j times sine, and then the 1/2 knocks out to 2. So it's sine j times what's remaining, which is nice because that's just again a delay by 1/2 sample. Now the j is something because the j actually is going to be a, so I can write this in complex form, right? That j is e to the j times pi over 2. So I can at least get it in the same form as my phase. So what this is called generalized linear phase. This is a phase response that does not go through the origin, but is a line. And if we apply the group delay definition, which is to take the derivative of the phase, this constant goes away when I take the derivative with respect to omega. It doesn't affect our group delay. The group delay remains 1/2 sample. So that's 2.1 on homework, parts A and B. All right, see you next time.
Did you rate a sine wave at like a kilohertz? There's multiply it by that.